For more information, please visit SGMAK Associates website.
Let us talk about random variable. Let me start with some examples of random variables related to a manufacturing or a service system. Interarrival time, processing time, quality of output, time between machine failure, and machine repair time. These are some examples. How often part comes to a system, how long it takes to complete a cycle. As you make parts or prepare documents, what's the quality? Machine fails from time to time. If you capture the time between failure, thus all these are examples of random variable. We can represent a random variable either as a discrete or a continuous random variable. This you have to be very clear about this distinction. As you identify a random variable, it has to be either a discrete or a continuous random variable. Now, if a random variable measuring time, volume, mass, or area, if you have one of those situations, you are dealing with a continuous random variable. So, volume of a part made by a manufacturing process, it will have a nominal value, but then have a variation because of the process itself. So, the volume of actual part can be treated as a random variable. Anytime you're measuring a time, in the previous slide we talked about time between arrival, time between machine failure. These are all examples of continuous random variable. Discrete random variable is easy to identify. A very simple example that you can relate to is number of parts made over a specified period of time. If you have an automated machine and that can give consistently output, then it becomes a deterministic number. But if you have a cycle time that is affected by variation, then output over a fixed period of time can be treated as a random variable, and it has to be treated as a discrete random variable because you get a discrete number as an output. Number of customers arriving at a fast food restaurant during the lunch hour. If you take a lunch hour 11:30 to 12:30 and watch how many people coming in a local fast food joint, if you collect it over a period of a week, you find that there is some variation. Every day will not be the same number. But what you're counting is how many people came in through the door during that 1 hour period. And you'll find that you have to treat that as a discrete random variable. Now, two important concepts dealing with a random variable are probability mass function and the cumulative distribution function. Now, for a discrete random variable, we call it probability mass function. If you're dealing with a continuous random variable, we call it a probability density function. But whether you are dealing with a discrete or continuous, we have a cumulative distribution function. So it's very important to understand the difference between a probability mass function or density function and the cumulative distribution function of a random variable. The cumulative distribution function plays a very important role if you have to generate random variable from a specific distribution. So if you later on take a course in simulation, you'll be using that a lot. Let's talk about probability mass function, the definition. The textbook definition, probability mass function of a random variable is simply gives you the probability for a specific value for the random variable. So as I've shown here, small p of x of I is the probability the random variable x takes a specific value x of I. And we are talking about a discrete random variable. So random variable takes on discrete set of values. A probability mass function must satisfy the following two properties. It's very important to understand them. First thing is your probability mass function should never return a negative value, or and should never return a value greater than 1. Probability is always a measure between 0 and 1, a number in the range 0 to 1. So probability that random variable takes a specific value should always be greater or equal to 0. And if you sum over all values the random variable can take, that summation should always be equal to 1. Now the cumulative distribution function is represented by capital F of x. That's the standard notation. You pick up any book on statistics, that's the standard notation for CDF. And the basic definition, f of x, is probability the random variable takes values less or equal to that specific value x. But if I state another way, f of k is the probability the random variable takes all values less equal k. So you're summing individual values for all values the random variable less equal k. Since you're summing, that's why you call it a cumulative probability. You're accumulating probability over a set of values for the random variable. A cumulative distribution function, whether it's for discrete or continuous, must satisfy the following. First, the cumulative distribution function returns cumulative probability, so it has to have a value between 0 and 1, both inclusive. Another important property is it must be a non-decreasing function. So if I have two values for the random variable x1 and x2, and x1 is less equal x2, then cumulative probability for x1 must be less equal to the cumulative probability for x2. There's a very simple understanding here. In cumulative probability, you're simply adding probability for a specific value of the random variable. If the random variable doesn't take a specific value, the probability assigned is 0. So when you accumulate them, and since probability cannot be negative, you cannot have a decreasing function. So that's why you call it a non-decreasing function. CDF, the cumulative distribution function, should always be a non-decreasing function. Let's take an example. You toss an unbiased coin 2 times. Coin cannot have only 2 outcomes, head or tail. You're tossing it twice. And you define a random variable, x, that represents the number of heads shown in a trial. Your trial consists of 2 flipping, flip twice. So if you write out the sample space, which is defined as the collection of all outcomes of an experiment. So we toss the coin, we are tossing the coin twice. So the sample space will have, in terms of outcome, head or tail. We can have both head, we can have first head followed by a tail, or a tail followed by a head, and both tails. So there are 4 possible outcomes. So that's how the sample space look like. Now, we have defined the random variable as the number of heads shown in a trial. As the number of heads in a trial, if you look at the sample space, number of heads can be 0, there are two outcomes when you have number of heads equal 1, and there's one outcome where you have number of heads equal 0, and one outcome when number of heads equal 2. So following that, if you look at those outcomes and count them, we can say probability that the random variable x takes a value 0 is 1/4, because only one outcome out of 4 is favorable to this event. Following the same reasoning, probability that random variable takes a value equal 1 is 1/2, because two outcomes show one head. So 2 out of 4 is probability 1/2. Same way, probability the random variable takes a value equal 2 is 1/4, because only 1 out of 4 outcomes is favorable to this particular event. So this is how the probability mass function looks like for this random variable, flipping a coin twice and defining the random variable as number of heads in a trial. Now if you want to convert the cumulative distribution function from this probability mass function, then we write it as f of x is 0 for x less than 0, because it's not defined. X cannot take a value less than 0. 1/4 for x between 0 and 1, greater equal 0 less than 1, 3/4 greater equal 1 less than 2, and 1 for 2 or more. Again, the cumulative distribution function represents the cumulative probability. So when you look at f of 1 as 3/4, it represents probability the random variable takes value less equal 1. That means we are summing up two values for x equals 0 and x equal 1. So that's why you get 3/4. When you find f of 2, probability of all values of x less equal 2, so you're counting x equals 0, x equal 1, and x equal 2, and that adds up to 1. So that's how the CDF cumulative distribution function look like. I have attached a separate handwritten sketch of this probability mass function and the cumulative distribution function at the end of this presentation.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.